Okay, good. Yes. So, yeah, for today then, we are looking at, this is lecture 3. So now we are looking at, so let's see, let them O13 be the algebra of S of O13 of the Lorentz group. So this, as we saw, is a 6-dimensional real algebra. Dimension over R is equal to 6. And so the notation here is O13C. By definition, I say this is equal to O13 tensor C. So this is the complexification of this real algebra. Right? So it's a 6-dimensional complex real algebra. And also we need SU2 the Lie algebra of capital SU2, right? The Lie algebra of capital SU2. So this is a real Lie algebra of dimension 3. Dimension of this guy over R is 3. And we also want to complexify this. So then we just say SU2C to be equal to this guy SU2, and so C. That's also complexification. So we took these two real Lie algebras. One of them is dimension 6, the other one is dimension 3. We complexified them. Now the point is we want to prove the following decomposition theorem. So that's the key for all these classifications of representation theory of Lorentz Lie algebra. So the idea is that O13C is isomorphic as the direct sum of these two copies of this U2C. So this is a Lie algebra isomorphism. So I will recall the definition of direct sums of Lie algebras, but in case it's a question. But that's an isomorphism of Lie algebra. So this is the key construction we need in all this all the representation theory that we're going to. Okay, question? Yeah. So the proof really, it's not difficult, but I mean, okay, so we have to know something to prove. So what we're going to do, we are going to introduce 3 boosts and 3 rotations. So 3 boosts, or I would say 3 rotations first, and 3 boosts. So let me tell you what I have. So rotations are, by rotations, I mean these 2x2 rotations in just a 2-dimensional Euclidean space. That's a very simple thing. So by rotations, I mean something like this. Our theta is equal to, so a cosine of theta, sine of theta. And here we've got sine theta. I would say minus sine theta and then cosine theta. You see, this is an orthogonal matrix. It's a rotation in a 2-dimensional Euclidean space. Right? So then we can just use this to define an infinitesimal rotation or an element of the Lie algebra that's tangent to this family of curves in the Lie algebra. Because Lie algebra is tangent to the Lie group, right? So what we can do then we can differentiate that at identity at 0. If you differentiate this curve of matrices at identity, which corresponds to theta equal to 0, then you're going to get, well, what is the derivative of cosine? Minus sine. At 0 is 0. Derivative of minus sine is minus cosine. At 0 is negative 1. Sine is cosine is 1, and this is. So that's this matrix, which is the element of the Lie algebra, SO2, basically. Now, what are the boosts? So maybe this is new. So boosts are analogs of orthogonal rotations, but in relativity theory. These are in a space T and X. So what is boost? So let's call it, maybe call it P theta or P theta. So this is the following thing: cosine hyperbolic of theta, and then we have got just to make sure the signs are correct. Cos theta, sinh theta, and sinh theta, cos theta. So the relation that cos squared theta minus sinh squared theta equal to 1, the hyperbolic trigonometric relation, this implies that E theta is an element of the two-dimensional Lorentz group. It belongs to the Lorentz group, which is, you can think of R2 and this quadratic form T2, I mean x0 squared minus x1 squared. In other words, it preserves this. So to check this, you have to check that the norm squared in this sense of the first one is 1, and norm squared of the second one is minus 1, because it's this one. And they are orthogonal with respect to the Minkowski metric inner product, which they are. That's all. Exactly what you do here to check that our theta is orthogonal matrix using sine squared theta plus cos squared theta equal to 1. You have that analog over there for. So these are called boosts because this is the you have seen a version of this which is in terms of the speed, relativistic speed. Maybe you can write it. I have it somewhere. If I find it, I will show it. Yeah, I have it. So this boost then.
There's a note. I think you're out of reach of the camera there.
Oh, I'm out. Oh yeah. So maybe I'll get that for now, and then I make sure that I won't leave out the spacing. Okay, so yeah, so these are the boosts. So you have seen this formula not in terms of, I mean, if you have taken special relativity, not in terms of Cauchy and sinh, but in terms of v over square root of 1 minus v2 and 1 over square root of 1 minus v2. The formulas that are due to Lorentz, Lorentz contraction and Lorentz dilations. It's exactly that one, but in a different coordinate system. Okay, so then similarly here, we can also differentiate these at 0, and then you get a matrix, infinitesimal generator of the boost, so which is the derivative of Cauchy is minus sinh, which is 0 then. The derivative of sinh is Cauchy, which is 1. So we get this one. Okay. So these are both stories now happen in two-dimensional space, but now we can just use these things to construct 3 elements, 3 rotations in this 4-dimensional space and 3 boosts in the 4-dimensional space in the following way. So let me show you how this can be done now. Okay, so the idea is the following. Go back to R4. So this is like x0 coordinate, the time coordinate, and orthogonal to the time coordinate are just three space coordinates. So this I call it x0, x1, x2, x3. Okay. So what we're going to do, we are going to take two-dimensional planes in this three-dimensional space coordinates. So we are going to take now rotations in x1, x2, x1, x3, and x2, x3 coordinates of planes. So of course they are not going to touch the other coordinates. They're going to keep fix the other coordinates, only each time they just change these things, right? So what we're going to get then, we are going to get, for example, in this case, we get and the infinitesimal generators. The infinitesimal generators. Now, for example, for this one, it's only touching x1, x2 coordinates. It leaves x3 and x0 unchanged, right? So we get the following matrix. So here is 0. Here for x1, x2, we get this 2 by 2 matrix. You remember what it was? 1, minus 1, 0, minus 1, 1, 0. And then, okay, and then there is 0 here. So it doesn't do anything on x3, doesn't do anything on x0, but on x1, x2 changes. Right? And then for x1, x3, we get some matrix which is like this. So, okay, always 0 here because time doesn't change, but x1, x3. So x1 is going to be something like, so 0 here. And then, okay, so should I draw all these things? It's kind of, you can figure it out.
Yeah.
Because I'm pretty sure I'm going to draw very ugly pictures here if I. And similarly, so let me cheat. I say similarly for other generators. And we also do a similar thing for so boosts so we look at boosts in x0, x1 space. And it's infinitesimal generators. Generator, which is going to be the following thing. In this case, it's going to look like how it's going to look like the following thing, as you remember. So there was the 0, and then we have 1, 1, 0, and then 0s. So there's a 2 by 2 component there, and the rest is. And then we do for x0, x2, and x0, x3 boosts. And similarly for x0, x2, x3 boosts. So these are basically the core of the thing. So we have really 6 preferred generators or six preferred elements inside this 6-dimensional real Lie algebra. And these are really a basis, form a basis for this Lie algebra. That's just simple algebra you can check. And we are going to use these things, but in a complexified form, because the isomorphism that I wrote, I wanted to prove the term is not true in the real case. Isomorphism has to be done in the complex case. So the isomorphism then looks like this. All right, so then get 6 elements. Again, we call them boosts and rotations, but they are not quite the same. But they are up to 1. Then get 6 elements in O13 complexified. The complexified Lie algebra as follows. So we call, for example, J1 be the following matrix. It's just I times so here is 0, 0, and then we have got 0, -1, and 1, 0. Okay, so what is it? This is a rotation in x2, x3 plane. Doesn't move anything. It's an infinitesimal generator, except I have also changed the sign here. So we can just say -I times that infinitesimal generator, which is here. Because my generator was 0, 1, -1, 0. But here is this one. So you can just put -I here and get exactly the same generator. Okay. Okay, so yeah, and then we get J2 and J3 in a similar way. And then we have to put K1, K2, K3, the infinitesimal quotient. And then we get K1, K2, K3 now. For example, K1 is the following element, I times, or I would say -I times. So this is 0, 1, 1, 0, and then 0, 0, 8. This is 0, 0. This is K1. Which is that generator in the real case, but multiplied by -I. And K2 and K3. Similar. Okay, so now we have got 6 elements, J1, J2, J3, and K1, K2, K3 inside the complexified Lie algebra. So we have now 6 elements. K1, K2, K3, and K1, K2, K3 in complexified Lie algebra. One of the first interests of these elements is that because they form a basis, actually, there's a basis, forming a basis. Forming basis. Now, if you look at exponential map from this Lie algebra into the Lie group, so you get exponential map from actually from the real part, O13 to SO13 plus. You see, The exponential map, we know that can only go into the connected components. It is missing other components because this space is just a vector space and is connected. So its image is going to be connected. So it just goes there, right? And this is so one of the nice things about this Lorentz group is that the exponential map is actually surjective. I mean, this needs a proof. It's not obvious, but it is true. It's surjective. For some Lie groups, exponential map is surjective into connected component of identity, and for some is not. So there are some phenomena you can check in general what can be done, but basically, in this case, that's the case. So it means that any Lorentz transformation in this component can be written as, so this implies that any matrix U belonging to, I mean, I would say A belonging to SO 1, 3 plus can be written as exponential of, okay, so now here I have to put back I again, sigma I, okay, I mean, these two I's are different, sorry. So I would put -1, I from 1 to 3 plus sigma 2 minus 1 ji. You see, I put back those i's again so that now this element is in the real layout. And this is just this, we are checking that. Because I claimed actually that these are the, I mean, without i's, they are really a real basis for the real layout. Question?
What did you have to look at the complexification of this?
Sorry?
So why did you have to look at the complexification?
Oh, yeah.
What was the significance?
Yeah, that's right. Indeed, something, yes, indeed, that's a very good question. See, something very strange happens. Because when you look at the Lorentz group, it has signature T2 minus X2. But if you complexify, if you go over complex coordinates, T2 minus X2 and T2 plus X2 make no difference. You can multiply by I and you go from one to the other. So over complex numbers, there is only one type of quadratic form, non-degenerate quadratic form, which is sums of squares. So if you complexify, you have a feeling that the difference between orthogonal and Lorentz is going to disappear. And in fact, this is what happens because this SU2 is very much related to, I mean, by decomposition at first we are trying to prove, is very much related to orthogonal group. But Lorentz is very much about this quadratic form, which is a signature. But once we complexify it, there's a chance to prove that actually they're going to be the same. Yeah, indeed. So there are these isomorphisms that are depending on complexification. Any other question? Nathan?
To get back to the other generators, should
Yes,
one
yes.
of the exponentials have a minus, should it be minus I
Or oh, by the way, I mean, I made a mistake. I mean, I should have put some coefficients here.
Oh.
Yeah, that's what you have in mind, right? Yeah, indeed. I can put some alpha I, some real numbers here, and then some real numbers here, right? Actually, maybe I could put theta I and beta I, something like that, but some beta I maybe. And that's what it is. That's what you have in mind.
Okay, yeah. Okay.
Yeah, exactly. No, I mean this. Sorry. I should have. Because this is just only one element. I mean,
Yeah.
it generates only one element. Yes, indeed. Okay. So this is a side, I mean, remark. I mean, it's not very essential right now. But what is essential is the kind of relations that these elements play, commutation relations between them. And that's very crucial. So I just write here. commutation relations for between J's and K's. So next, we have to observe that Ji and Ki satisfy the commutation relations so these JI's and JJ, it's the commutations that they satisfy is in terms of yes, they satisfy commutations in terms of the Lorentz symbols equal to I times epsilon I jk. Now, what is this tensor epsilon I jk? I mean, this is summation is understood. So epsilon I jk is equal to 0 if two of the indices are the same. Equal. And otherwise is equal to the signature of the permutation, pi, epsilon 1 to 3, where pi is the permutation. Pi of, I don't know, 1 equal to I, pi of 2 equal to j, pi of 3 is equal to. So this is called Lorentz symbol. It's a tensor, I believe, in some exterior space, but that doesn't matter. So this is the Lorentz symbol, and this is this one, this relation. Now these are called angular momentum relations. I mean, this is known maybe from quantum mechanics or from angular momentum. So these are the angular momentum relations. So these are exactly actually relations that are satisfied by fundamental generators of SU2C. Okay, so these are commutation relations. I believe in physics they call it angular momentum algebra, but that's a commutation relation. SU2C. Now these K's also satisfy a similar thing with minus I only. Also, we have this Ki and Kj equal to minus I epsilon I jk. K sub k. Yes. And between the two, Ji and Kj, there is a relation which is I times epsilon I jk, jk. So we have this relation, and this relation. So we have three sets of commutation relations between these 6 elements inside the algebra. And we notice that so there is it looks like there is a copy of SU2 is generated by this case, and a copy of SU2 is also generated by this one. But the difficulty is that they do not commute. The commutation of this thing and that thing is 0. It's not 0. And so it means that we cannot just send those elements into different parts and then drive the commutation, drive the decomposition, just like that. So you have to do something now at this stage. You have to get creative again. So this is a bit like in complex analysis. you write a complex number as a linear combination of its real and complex parts. So what we can do in this case, we can define to handle this problem of non-commutation of J's and K's, we can just define new matrices. You know? So there are different notations people use. Some people use, Ji plus. So let Ji plus now, by definition, to be equal to 1/2 Ji plus Iki. And Ji minus equal to half of Ji minus Iki. Yes. Then using 1, 2, 3 here, you can check that they satisfy exactly the kind of commutation relations you want. Using 1, 2, 3, we can conclude that in fact Ji plus Jj, I would say, yeah, Jj plus is equal to I epsilon I jk plus, and then Ji minus commutation Jj minus is equal to I epsilon ijk jk minus, and between plus and minus the commutation is 0. That's the magic. Ji plus Jj minus for all. And that's it. So once we have produced these things, and if we agree that these matrices form a basis for SU2 complexified, then we have got a map now. The corollary of this is that we have constructed a map from the complexified Lie algebra of the Lorentz group, Lorentz Lie algebra or Lorentz algebra, into this C, Helix on SU. That's the end of the group. That's the so forth. Yeah. Good. So, any questions or comments?
What did complex analysis do you use this trick? I'm trying to.
Oh, I meant you write something like this. Yeah. A good question. You asked good question. That's very good. So you see, when you have these differential operators, like dz, for example, is 1/2 ddx minus I dy, and ddz bar, yeah, is equal to 1/2 ddx plus I dy. And of course, Cauchy-Riemann equations just says that for a holomorphic function, ddz bar of f equal to 0. That's I had in mind. I mean, you have these two operators, ddx and ddy. You cook up two new operators, ddz and ddz bar. So it's a bit like this.
Yeah.
Yeah. So and then I mean, somehow these are much better operators than ddx and ddx. I mean, I cannot give more analogy. I don't think there's more to this, but maybe there is, but I don't see. But this is sort of the composition. Maybe there is an algebra that takes care of this idea in general. You have two things that is written in a basis that they don't look like orthogonal, but you can actually show that they are orthogonal to each other if you choose the right basis for spaces, something like that. I'm not sure.
Yeah, because it does seem like magic when you start with two things like opposition. They're not orthogonal.
Yeah.
Two, right? And then
Yeah.
it's a very convenient transformation.
Yeah, in random matrix theory also we use this sort of decomposition for Hermitian matrices, right? I mean, in terms of real and complex parts.
Yeah.
When we write the Lebesgue measure in terms of the two things.
Yeah.
Or something like that. Yeah. Any other question? Okay. So now that we have this isomorphism, so we can just use some general facts about representation theory of Lie algebras and to reduce representation theory of this very complicated algebra in terms of these two. So just to motivate this, let us take a simple example, actually from maybe representation theory of groups even, or finite groups even. So kind of motivation. Let G1 and G2 be finite groups. And rho 1 from G1 to GL V1, rho 2 from G2 to GL V2. These are irreducible representations, irreps. Then from here we get an irreducible representation for Cartesian product of G1. We get rho from G1 plus G2 to GL V1 tensor V2. Well, this rho of G1 V2 acting on like V1 tensor V2 is equal to G1 V1 tensor G2 V2. Now this we know from finite dimensional representations, for example, of finite groups. And amazing fact in this case is that actually, if rho 1 and rho 2 are irreducible, then this is also irreducible over complex numbers. Well, I mean, actually, this direction maybe is true in general. So rho 1 and rho 2 irreducible implies that rho is irreducible. But even more importantly than this, any irreducible representation of the Cartesian product is obtained this way. So this is quite interesting. Conversely, any irrep of G1 plus G2 is obtained. Right? That's something good to know as a motivating example. And something similar to this happens for finite dimensional, for example, Lie algebras. So I can just say similarly for G1 and G2. Oh, okay. So this is, I should say, this is over C. You have to be over complex number. This is not true over real numbers. I mean, similar for G1 and G2, all irreps are obtained by taking two irreps of one for G1 and G2 and then forming the tensor product. So let me write it. um, all Europe's G1 direction G2. You see, this is like I mean, I could have said cross product. This is like an analog of this Cartesian product in this case for the algebra of this one are obtained as, so we have got to go from G1 with some G2 to and the morphism of V1 tensor V2, where here we have row of x1, x2 acting on this vector V1 tensor V2, typical vector. Now, we have to differentiate this relation at identity. When you differentiate this relation, you're going to get x1 v1 tensor v2 plus v1 tensor x2 of v2. I mean, I could have written row of x1. Here, this means really row of x1 acting, and this one is row of x2 acting. But that's, you understand. Okay, so, well, okay, so I just say orally where this one is an irrep of v1 and this one is an irrep of v2 over complex numbers. This is also true. I mean, it needs a proof. It's not obvious, but it's a standard in representation. So now the upshot is that if we want to understand all irreducible representations of this complexified Lorentz algebra, we have to understand irreps of SU2C. That's all. Oh, I have power. That's good. So then the corollary of this is that understand. I mean, to classify. Let me put it like this: to classify irreps of finite dimension irreps of O1 we C need to understand, need to classify irreps of SU2C. Because this guy is a direct sum of these two things, so we have to understand these irreps. Right? Okay, now, but this is very standard subject. We know these irreps, so let me tell you quickly what they are. In fact, this is in one-to-one correspondence with representations of SU2, the capital SU2, complex representations of SU2, because SU2 is simply connected. So this is in one-to-one representation with complex irreps of SU2. These are complex irreps of SU2. So what are they then? What are all complex irreps of SU2? What are they? So there are many presentations of these things, but there is one. So okay, from I start from SU2, capital SU, the group from SU2 to GL VK. So here K is equal to 0, 1, 2, 3, so on. So what is VK? We have to specify that vector space VK. What is VK? VK is a space of polynomials of degree K in two variables Z1 and Z2. So So this Vk, the space of homogeneous polynomials of degree k in Z1 and Z2. So basically, K is the set of all, like alpha K, I would say alpha I, Z1 the power I, Z2 to the power K minus I, and then I from 0 up to K, right? These are all the possibilities, right? And of course, dimension of Bk is K plus 1, right? It's K plus 1. Dimension of Bk is K plus 1, but we like to write it as 2s plus 1. So we just introduce an s, we call it s such a number that 2s plus 1 is equal to K plus 1. So s is equal to K over 2. So that's called the spin of the representation. Spin of the representation. Okay. I'll get to that, the spin, very soon, but this is just for us, just a notation. But now, what we need to do, I have to define what is the representation. I haven't defined how it acts. But that's clear how it acts, because you see, SU2 is acting on C2, right? SU2 acts on C2. So this is like linear polynomials in degree 1, alpha 1 Z1 plus alpha 2 Z2, right? Like alpha 1 Z1 plus alpha 2 Z2. It's a space of such linear polynomials, right? It just sends a Z1 into that matrix acted on Z1, and so we identify the first coordinate E1 with Z1 and the second coordinate E2 with Z2. So obviously SU2 acts on this. And now, so it acts also on polynomials by pullback. It acts on polynomials by pullback. So in other words, so if this is rho K, if I have a matrix, how does it act? How does this matrix act now? So I mean, rho K of some matrix A acting on a polynomial P. If you want to know its value at Z1, Z2, this is the P of A inverse of Z1 and A inverse of Z2. Because it has two variables, that's the way it acts. The way that if you have an action of a group on a space, then the group acts on functions on the space. So there is actually a fancy way of telling what this representation is. Let me write it kind of in fancy language, a little more fancy, not too fancy. So let's rho 1 from SU2 to GLC2, just a standard representation, because SU2 is 2 by 2 matrices. It acts on C2 of this standard representation. Which corresponds to this case, by the way, corresponds to a spin 1, okay, a spin 1/2 case, S equal to 1/2 case. Okay, so this is rho 1. Now, what is rho K? Rho K is the kth symmetric power of rho 1. Rho K is equal to Sk of rho 1, kth symmetric power. Symmetric power. So in other words, Vk is Sk of V1. Is the kth symmetric power of V1. This is Vk, and it induces on this tensor products and symmetric tensors. This is kind of fancy language, but it's the same thing. So now, in representation theory of Lie groups, they show you that actually these are irreducible, and these are all of the ellipses of SU2. So, fact is that these are all ellipses of SU2. So another fact is that for a spin half, or half integer spin, for s equal to 2l plus 1 over 2 half integer, these representations that do not come from SO3, okay? These reps do not come from SO3. You see, the reason now I'm saying SO3 is the following, because as we discussed, a spin SU2 is a spin 3, right? That's something that I'm not sure I mentioned, but this SU2 is really a spin 3. And we have this, actually I constructed this thing, so SU2 in last lecture, similar to this construction of the using spinners in the 4x4 case. In the 4-dimensional case, I use spinners to 3 Pauli spin matrices in the 3-dimensional case. So we go from the SU2 to SU2. So that's the universal covering. So obviously, if you have an irreducible representation here, rho, right, with GLB, you can pull back, you get an irreducible. But if you have a representation here, it does not necessarily come from something like this. And what this says is that for half integer, they do not come from representations of SO3. The lifting does not exist. But for even a spin, they do. But they do come from ellipson. So it's really for s equal to equal to So, and in fact, what happens is that this also classifies, I mean, believing in all this, this also classifies ellipses of SO3. There are half of them. The ellipse of SO3 is just half of the ellipse of SU2. Only integer spin ones. There's just half of them. They are here, but the rest are. Okay, now, so because this guy is simply connected, you can. So from here you get ellipse of Lie algebra SU2 and SU2C. How? You just differentiate these ellipses at the identity of the group, then you get ellipse of Lie algebras. There are formulas, but I didn't write the formulas, so I cannot reproduce the formulas for you now. But basically, what the upshot, I have to give one more lecture to give some examples now, because we have proved something very interesting. So then the representations of Lorentz group, Lorentz Lie algebra, complexified Lorentz Lie algebra, comes into pairs. One is spin for this component, another is spin for that component. So now this I just write, and then we come back to this in the next lecture. So the corollary is that they are they are classified by pairs of indices, not just one, but pairs of spins, not one spin. Right, so corollary is that ellipse of O, 1, 3, C are classified by a pair S1, S2 of indices of spins. So the dimension of this representation, its dimension or of course dimension of this 2s1 plus 1 times 2s2 plus 1, right? Because we just took the tensor product of two representations, and for this one is 2s1, the other one is 2s2, 2s1 plus 1, the other one is 2s2 plus 2, and then okay. Now we have to go on and construct some examples so that you know what are the Weil spinors, what are the Majorana spinors, what are the Dirac spinors, in which representations they are located. And we'll see that Dirac, for example, is not irreducible. And so there is some terminology that physicists develop, and I hope we can understand that because it's kind of effective, useful. So I think for now it's good enough. If you have questions, I'll be happy to entertain the questions. Yeah.
Big question.
Yes.
Does the trace or offer the determinants of these representations give us something similar to finite group case, or determinants of these representations, finite group case gives us character.
Traces.
Trace, yeah, that's right.
Traces, yeah. Yeah. Oh, yeah. I mean, characters. I mean, indeed, if you want to prove one of those theorems, you have to use the character theory. That's the easiest way to prove this, using character theory for Lie groups, actually, in this case. Yeah. And there are some similar things. For example, you want to prove that this guy is semi-simple. The Lorentz group is semi-simple. Any finite dimensional representation decomposes into direct sums of irreducibles. This sort of facts, again, you have to use sums. I mean, one difficulty here is that this group is not compact. The Lorentz group is not compact, so a lot of things you have to be careful. But there are tricks because you can work also with the compact, maximal compact subgroups and use that. But if you need some, any other questions? Or? No? Okay, I said anyhow I can stop the video.